Hi everyone, my name is Anthony Malumbe and welcome to my KaggleX Mentorship Program Showcase, where I will walk you through my project. The rapid detection of chest infections from chest radiography images using convolution neural networks. A little bit about myself. I am a business agility manager at Accenture and an aspiring data and machine learning engineer. I am the apprentice co-lead for the technology degree apprenticeship program at Accenture, where I lead a team who play an instrumental role in sourcing, fostering, and mentoring the next generation of technology talent from disadvantaged backgrounds. In my current role as a business and data agility coach, I help my clients to embrace agile ways of working and becoming more agile in their approach to managing and using data effectively. But what truly drives me is my profound love and fascination for cutting edge technologies with a current focus on deep learning. So, why did I choose this topic? In the UK, the flu season typically starts in October, with the peak flu infections occurring between December and February. The sudden spike of infection volumes leads to an increase on demand for the healthcare services. According to the World Health Organization, there are around a billion cases of seasonal influenza, of which COVID-19 is a variant annually, including 3 to 5 million cases of severe illness. Influenza causes between 300,000 and 600,000 respiratory deaths annually. The current gold standard for testing influenza cases is by using PCR tests. They are quite accurate, with a false negative rate of less than 5%. However, PCR tests must be sent away for analysis at an accredited lab. This increases the lead time for diagnosis. The project delivery framework and workflow consisted of the following key stages: planning and problem definition, data engineering and data analysis, MVP and model development, model engineering, serving, monitoring, and maintenance. The objective was to create a mechanism for swift notification to clinicians for potential influenza or pneumonia cases, whilst minimizing false positives and negative predictions to ensure accuracy. The requirements were to collect a diverse dataset of X-ray images, to develop machine learning models, and to use the following evaluation matrix like confusion matrix, precision, recall, and F1 score to validate the models. The data source used to build the ML models consisted of 33,920 chest X-ray images with a corresponding 33,920 lung masks. The data source was compiled by researchers from Qatar University and is available at Kaggle. Whilst analyzing the dataset, it turns out the dataset was stored in two separate folders: the lung segmentation and infection segmentation. Both folders consisted of X-ray and mask images. The lung mask images were removed to improve gradient descent and model training. The lung segmentation and infection segmentation datasets were both combined to increase training and validation datasets. The X-ray images with random labels were removed as they could not easily be labeled visually. This left about 20,628 images with the COVID, non-COVID, and normal labels for model training. Different data augmentation techniques were then used to enhance the diversity of the images. These were random scaling to simulate differences in image resolution, random cropping to simulate variations in regions of interest, random shearing to apply random transformations to mimic distortions that can occur during X-ray acquisitions, random brightness and contrast adjustments to simulate variations in image quality, sharpening filters to enhance image detail, and combinations of rotations of the images, and combining two images to create a new image that blends features from both. And lastly, random erasing a portion of the image to encourage the model to learn from other regions. During the MVP stage, a decision was made to use transfer learning over building models from scratch. This reduced the times it takes to develop a model, improved generalization, and reduced chances of overfitting. 5 pre-trained models were selected from the MVP stage: the DenseNet 201, Ensemble, Exception, EfficientNet B0, and EfficientNet B7. The models were developed using Google Colab Notebook and stored in this GitHub repo. Grade and COM was used to try and understand the decision-making process of the ML models during prediction. Gradient COM is an extension of COM that utilizes the gradient information flowing into the final convolution layer. It provides a more precise localization of important regions in the image to the model. Of the chosen 5 candidate models, it turns out that the following 3 models, DenseNet 201, Ensemble, Exception models, tended to either overfit or lacked convergence. This meant the predictions were poor and the validation loss was stubbornly high, even though the accuracy of the models were high. The efficient NetB7 model was very effective at accurately predicting COVID cases on unseen X-ray images. It turns out the fast AI, efficient NetB7 pre-trained models, false negative rates were below the industry benchmark for PCR tests on COVID testing. The model is deployed in Gradio app and hosted in Hugging Face spaces. When you go to the app, you will notice a selection of X-ray images already preloaded for you. When you select an image, a prediction is provided to you. You can also select an image of your choice by going onto an area where you've got the image located, and you double click on the image and you select it and you click submit and the prediction is provided for you. Thank you for listening.